Welcome to our instructional statistics video for Stat 333, University of Waterloo Math course. We're here basically to illustrate a Markov chain problem for you, and we wanted to take a real life example and turn it into how it works in terms of a Markov chain. So what we tried to define today is a game called pseudo squash. So for those of you who don't know how the game of squash works, usually squash works up to the first player to get 9 points. I'm going to keep it simple and just say it's the first person to get 2 points. Basically, there's two players. If I'm player A and I have a friend over there who's player B, I can only score a point if I'm the one who's serving. So the person who's serving, he can score points. In order for the other player to get serve, he must beat me in a rally. So squash is just a bunch of rallies. Whoever scores and wins the rally, that determines who's going to serve. And again, you can only get a point if you're serving. So for example, here's our illustration. If player A is serving and wins the rally, player A gets 1 point. But if player A wins the rally but B was serving, he gets nothing. Now A gets the opportunity to serve. Similarly, if player B is serving and wins the rally, then B would get the point. But if B is serving and loses the rally, A now gets the opportunity to serve. So again, you can only score points if you're serving. So that's basically the definition of how the game works. And now we want to basically talk about the math behind it. So we got inspiration for this question from our Stat 333 midterm, where we defined the tennis game. The difference between the tennis game and the squash game is that anyone could win regardless of who was serving. Because we have a difference here, you can only score if you're serving, we had to define different probabilities. So let's define xn to be player A's lead over player B at any given time. So that means that since it's the first to win by 2, player A and player B, the max lead that they could have is 2, and the max deficit they could have is -2. And then we had to define 4 probabilities. P is basically the probability that A wins a rally, given that A was serving. 1 minus P would be the probability that B wins that same rally, given that A was serving. The other 2 probabilities are very similar. We define Q to be the probability that B wins if B is serving, and 1 minus Q to be the probability that A wins the rally, given that B was serving. So these are our 4 important probability definitions. The last definition that we have to do in order to make this a Markov chain problem was to define what our states would be. So our states have the form ij, and I is going to basically represent player A's lead or deficit at any given time. So since it first came up to 2, my worst deficit could be -2, I could have a deficit of -1, and I could go all the way up to a lead of 2. The j portion of our state represents who is serving. So that's really, really important. We need to know at each given state who is the server. And so our server, basically j will be from the domain A and B. So again, those are our states. Our probabilities P and Q are defined. And now we can go ahead and try to make this a Markov chain problem by defining the transitional probability matrix.
As Srin said, since we have a discrete Markov chain, we're going to define a transitional probability matrix. So let's go down row by row. So looking at the state where player A is down by 2, the chance of player A staying down by 2 is 1 because the game's already over. Looking at the state where player A is down by 1 and it is player A's serve, the chance of moving to player A down by 1 and B serve is 1 minus P, or the chance that A loses on the serve. And the chance of it becoming an even match is P. Looking at the state where player A is down by 1 and it is B's serve, the game is over if player B wins on his serve. And it moves from state -1B to -1A with probability 1 minus Q, or the probability that player A wins on B's serve. So looking at an even matchup with player A starting the serve, the probability of moving to player B's serve is 1 minus P, and player A being up by 1 is P. The initial matchup with B serving is B being up by 1, or A being down by 2 with probability Q, and moving to player's A's serve with 1 minus Q. And looking at the chance where player A is up by 1, the game is over with probability P, because as soon as you're at state 2, the game's over. And you move to player A up by 1 with B serve at 1 minus P. And looking at the player A up by 1 and B serve, the chance of moving to an even matchup with B serve is Q, and player A up by 1 and A's serve is 1 minus Q. And then obviously looking at the bottom case where player is up by 2, the game is over, so the probability is 1 of staying in that state. Since there's an equal chance of either playing starting first, the initial vector is 0, 0, 0, 1/2, 1/2, 0, 0, 0, corresponding to 0A and 0B.
So the last way to describe this Markov chain would be to use a state diagram. So Kyle defined for us the 8 different states, moving from -2 all the way down to a lead by 2. So for example, let's say I'm already losing by -2, the game's over. So the only way that you can move within this state is to move back to itself. So the probability of staying within the state -2 is 1. How do I get to -2? I need it to be losing by 1, but B needed to be serving, since only B can win a point if they're serving. So that's how we get to -2. The other thing is, if I'm at -1B, I could get to -1A should I win the rally. From -1A, of course, I could move back to -1B, but I could also move to 0A if I win the point. From 0A, similarly, I can move to 0B. If I'm serving and I lose the rally, then the other player gets to serve. And similarly, we could move back to 0A depending on who wins the rally. From 0B, we could also move, though, to -1B. And that's because if player B is serving, the game is tied, they can be up by 1, which puts me in a -1 deficit. And a similar pattern keeps going from here. And lastly, if player A has a 1-point lead and they happen to win that rally and they're serving, we can move into state 2. And of course, once we have a 2-point lead, we're going to stay there.
Alright, so now looking at the classes, we have the first class, which is the -2 state, and clearly that is closed. And the second class, which takes up all these states where the game is still going on, that state is open and transient. And the third class, state 2, is clearly closed as well.